Example number 2, and this will be our last example that we're going to be looking at in section 6.1. So I'm going to begin this problem. This is definitely a larger system, but I'm going to go ahead and begin this problem the same way as I did the last one. I'm going to determine the intercepts for these 3 linear equations or inequalities, okay? So for the first one, if we let x be equal to 0, we'd have our y-intercept, which would be what? What times 5 gives you 36, right? So y-intercept would be 0, 6. It doesn't matter the order in which you determine the intercepts, just be able to determine them. The x-intercept is determined by letting y equal 0. So that would mean x is what? X would be 5. So there's your 2 intercepts for the first equation. This one, if, let's just do it this way. If x is 0, then y is what? 6, good. All right, if y is 0, then x is 2, good. This one, okay, if x is 0, y is 4, right? All right, if y is 0, then x is 4, okay? So we have all our intercepts here. Now we just have to be able to plot those on our coordinate plane system, which I'll do here in just a second. This is really telling us what? X must be greater than or equal to 0, and y must be greater than or equal to 0. This really means that your entire shaded region, the solution, in other words, must be occurring where? This is really telling us the solution can only be occurring in quadrant 1. Okay, so let's go ahead and plot these points, and then we have to solve a couple of systems of equations here in order to determine our points of intersection. All right, so I have placed all of my intercepts on my graph, on my coordinate plane system. Now it's time to connect the dots. I did find my old ruler from 1913. So let's see if I can still use this. It's been a while, over 100 years. So I have lined it up. Let's draw our first line. Wow, magic. All right. And then which way would we shade this? Well, if you put in a test value, okay, if you put in a test value into this equation, this inequality, excuse me, notice we could use 0 here again, 0, 0. And 0 is less than or equal to 30. So that means we would shade the region that does include 0, 0. So everything below the line, in other words. Okay? So we'll do that in just a little bit. Next one we're going to draw is, let's see, what was the next equation? 3x plus y. Okay. So those intercepts would be what? 0, 6. And then 2, 0. So let's graph this line real quick. It looks something like this. And in this particular one, if you did plug in 0, 0 as your test point, you'd get 0 is greater than or equal to 6, which is what? Which is false. 0 is not greater than or equal to 6. So therefore, you would shade everything above and to the right of this particular line. Okay, so just keep that in mind. Our final graph is going to connect what? 0, 4 and 4, 0. So let's go ahead and do that. 0, 4 and 4, 0. And that will look something like this. Again, I hope you're noticing something else, that I'm only looking at quadrant number 1. I'm only looking at quadrant number 1 because of this information. All right? Okay, using the test point again, 0, 0, right, which is not a point on any one of these 3 lines, you get what? You get 0 is greater than or equal to 4. Is that true? No, it is not true. So because that's false, because 0 is not greater than or equal to 4, you would shade this way, above and to the right of that line. So when you put all the pieces of the puzzle together, you end up getting what for your solution region? Remember, it's only what is overlapping, it's only what is being shared that represents the final solution. So in this case, it's going to be this region right here. So everything in this area represents the solution region. All right, so this one is going to be bounded because it is possible to circle it. And we're missing one more thing. And this is not necessarily fun to do, but we have to come up with these. They're going to be called vertices soon enough. All right, you're going to have to be able to determine these vertices, these corners, if you will, that make up a bounded region, or even vertices that make up an unbounded region. Doesn't matter. We have to be able to determine these points. All right, so let's see if we can do that now. Okay, so in order to do this, we have to determine what equation matches up with this line and what equation matches up with this line. Well, just use your intercepts. So 0, 6, 2, 0, 0, 6, 2, 0, we're going to need this equation. And then we also need this equation that would have 0, 4, and 4, 0 as our intercept. So this equation. All right, let's go ahead and set up our system and then solve it to determine this point of intersection. Here is our setup. I went ahead and wrote them in as inequalities, but you just think of these as equations at this point. So I'll go ahead and do that in the next step. First line is going to stay the same. And the second equation is going to become what? A negative x minus y equals a negative 4. And I'm doing that so that our y components are opposite, so they cancel out. And then we're left with what? We're left with 3x minus x, which is 2x. 6 minus 4 is 2. 2. So therefore, x is 1. All right, if x is 1, let's just use this first equation. If x is 1, you get 3 times 1, which is what? 3. So 3 plus what equals 6. That's how you determine your y value, which is, of course, 3. So our point of intersection is going to be 1, 3. And let's see how good we did here graphically. Ooh, look at this. Every one of these, right, is 1 unit. So every 2 blocks on my graph paper, every 2 blocks on my graph paper is 1 unit. So this is 1, and this would be 1, 2, 3. Oh, brilliant. So 1, 3. You have to come up with these corners or vertices of your bounded or unbounded regions in order to be able to handle not only material in this section, but for section 6.3 as well. Hope you guys are staying well, staying healthy. Hopefully the weather is not too bad in your region. You're getting outside, taking a walk, doing something physical. I'll see you shortly for section 6.2.